Hello and welcome to part 4 of Newtonian physics, in which we're going to start to introduce hydraulic systems, because these work as a very useful analogy for electric circuits. The first concept I need to talk about is flow, rate of flow. Now, supposing I have a pipe, like one of the ones on the slide, and water is flowing along it, or whatever the fluid is flowing along it at a speed v, velocity v. Let's consider the volume of fluid that passes a certain point in the pipe in a 1 second interval. Well, if the velocity is v, then in 1 second, the distance that any bit of fluid has moved will be the velocity times the time. Velocity times time. If time is 1 second, then the distance is just numerically equal to the velocity. So if I go back a distance here, which is numerically equal to the velocity, so for example, if the velocity was 3 meters per second, then I would go back a distance of 3 meters, means that after 1 second, the part of the fluid that was here in the pipe will now be here in the pipe. Therefore, all of the fluid between this point and this point must have moved past this point in that 1 second. What is the volume of that fluid? Well, it's just d, the distance, times the cross-sectional area of the pipe. dA would be the total volume that's past that point there, or in fact any other point in the pipe, in 1 second. The volume passing a point per second is known as the flow rate. And it's measured in cubic meters per second. And it's equal to the velocity of the water times the cross-sectional area of the pipe. Right. On to pressure. Here we have a syringe. You press the plunger here, that increases the pressure of the fluid in the syringe, and that causes the pressure to leave out of the nozzle of the syringe. The pressure, as you may remember, is the force divided by the area. So it's the force being exerted on the fluid divided by the area over which that force is being exerted. Now, there's something very important to know about fluids under pressure, and that is the pressure doesn't have a direction. If a fluid is under pressure, then it exerts the same force on a surface no matter in which direction the surface is. The fluid is trying to push out in all directions. You can imagine it a bit like a balloon that's been blown up. It's pushing out on the surface of the balloon in the same pressure in all different directions. And the same is true of fluids under pressure. They push out with the same pressure in all directions. Okay. We can combine these two ideas and get a very useful equation relating the pressure to the volume of fluid moved and the flow rate. It goes like this. We know that the work done in moving an object, the work, is equal to the force exerted on the object times the distance through which it moves. Now, for a fluid, the force being exerted on the fluid is the pressure times the area. That comes directly from the definition of pressure. If pressure is force over area, then force must be pressure times area. So the work being done is the pressure times the area over which the pressure is being exerted. Now, the distance we can relate to the volume of water moved, because as we've just seen, the volume of water moved is the distance times the cross-sectional area of a pipe through which the water is moving. Okay, so the distance we could write as the volume of water divided by the cross-sectional area. So if we're considering about fluid moving in a pipe, which has a cross-sectional area of A, and a pressure P in the fluid, a volume, say, V of that fluid here, that's the volume in there, moves along the pipe, then we could say that the work that has to be done by the fluid on this side here to push that volume through the pipe has got to be equal to the pressure being exerted on that fluid, which is just the pressure of the fluid in this part of the pipe. Remember, pressure in a pipe pushes equally in all directions, including on this bit of fluid here that's going to move through the pipe in this direction. So we've got the pressure, we multiply that by the area over which the pressure is pushing, that's just the cross-sectional area of the pipe. Then the distance that we're moving is the volume of the fluid that has moved divided by the area. We can do that and get a useful formula, the pressure multiplied by the volume of fluid that has moved is the work that has been done to move that volume. And if we consider the rate of doing work, how much work is done in 1 second, then that would be the pressure, which we can assume is constant, times the volume that has moved in 1 second. And the volume that's moved in 1 second is, by definition, the flow rate. So the rate of doing work, the work done per second, is the pressure times the flow rate. And that's a useful formula. Right, quick thought experiment. Supposing we have 2 pistons like this, and we have a 10 kilogram weight pushing down on each of those pistons. The system is full of a weightless, incompressible fluid. I release the 2 10 kilogram weights. What happens? Do they move? If so, which one goes up and which one goes down? Well, consider this narrow section of pipe joining them together. In this part of the system here, the pressure will be exerted by this 10 kilogram weight pushing down. Let's supposing that the cross-sectional area of this piston here is, I'll call it AY. It's got a 10 kilogram weight pushing down, so the pressure that's being exerted by that force acting over this area would be 10 kilograms divided by AY. That would be the pressure in this side of the system. On the other side of the system, I've got another arrangement, but this time I have a larger plunger in my cylinder of cross-sectional area AX, bigger than AY. I have a 10 kilogram weight here as well. That's going to be pushing down, and that's going to be causing a pressure in this part of my system of 10 kilograms divided by AX. So the pressure here is smaller than the pressure here, because AX is bigger than AY. That means I have a larger pressure on this side than I have on this side. So the fluid in the pipe is experiencing a force in this direction caused by the pressure here multiplied by the cross-sectional area of the pipe. Force here is bigger than the force going in this direction caused by this lower pressure multiplied by the cross-sectional area of the pipe. So the fluid in the pipe has a larger force this way than it does this way. Net result, it starts to move in that direction. And that means that this 10 kilogram weight here is going to go up as more fluid empties into this cylinder. And this 10 kilogram weight here is going to go down as the fluid leaves this part of the system. One interesting point about this experiment: what about work and energy? Well, we've just derived this formula that the work done is the pressure times the volume of fluid that's moved. The work done by the fluid in this cylinder will be the pressure at this point here multiplied by the volume of the fluid that has left this cylinder. The energy that is gained by this part of the cylinder will be the pressure in this part of the cylinder times the volume of the fluid that has entered this cylinder. You could, if you like, think about this cylinder as doing negative work, because the volume isn't leaving this cylinder, it's entering this cylinder. If you think about that as a negative volume leaving, then you could say the work being done by this cylinder is the pressure times the volume leaving, but the volume leaving is negative, so the work being done is negative. If you're doing negative work, then you're gaining energy. So this side of the system is losing energy by doing work, and this side of the system is gaining energy by having this fluid coming into it. Except energy is conserved. The work being done by this cylinder is 10 kilograms divided by AY, that's the pressure, times the volume leaving. The energy being gained by this cylinder is 10 kilograms divided by AX, the pressure in this cylinder, times the volume that's entering. But these are not the same, because AX is not equal to AY. So this is the work being done by this cylinder. This is the energy being gained, if you like, the negative amount of work being done by this cylinder. But the work being done by this cylinder is not equal to the energy being gained by this cylinder, because AY is not equal to AX. But energy is conserved. So where did the energy go? And the answer is, the energy went to heat up the fluid in this pipe. This bit of narrow pipe there. You can't do this without losing some energy from your hydraulic system. If fluid is going from an area of higher pressure to an area of low pressure, then it is losing energy from the system. And usually that energy goes into heat energy to actually heat up the little bit of fluid that's moving. Okay, that's enough about hydraulic systems as an introduction. We'll move on and we'll look at the operation of pumps and see how hydraulics relates to electric circuits.